Hey guys, it's Mr. Riz, and we're going to go over section 1.3, which is evaluating limits analytically, so that means working it out. We're going to take this section and break it up into 3 videos, or 3 parts, just because there's a lot. So, first thing we're going to do is evaluate limits using properties of limits, and we're going to use a technique called direct substitution, and it's pretty easy. So this first video, you might get confused just by how easy limits are for the majority. Okay, well here's the property of limit. Basically it says the limit of f of x as x approaches c does not depend on the value of f at x equals c. However, it's the limit precisely of f of c. So what's that saying is, just like before, we have a function. Sorry. What this is saying is that majority of the time what we're doing is when we're looking for a point, majority of the point is going to be directly where it is located on the graph. The only time that will not work is if when we plug it in we don't have an asymptote. But if we have a function that has no hole in it, it is going to be a continuous function. Alright, so basically, first part says 1, the limit as x approaches c of a constant b equals b. What that looks like is, say we have some function f of x equals 4, so the limit of f of x as x approaches 5 of 4 would equal 4. Next, limit as x approaches c is equal to c. So say we have a nice linear function. So we have a linear function, f of x equals x. The limit as x approaches 6 is going to be 6. And lastly, limit as x approaches c of x of n equals c to the nth power. And so that looks like x cubed to the third power. So we could have just, all we're going to do is take 3, plug it in for x. We get 3 to the third power, which is 27. So here's some more examples. If I'm taking 2, x as x approaches 2 of 3, I'm going to take 2 and plug it in for x. Since there's no x, it just becomes 3. This one I'm going to go as x approaches negative 4, so that means I'm going to plug a negative 4 in for x, which the function becomes negative 4. For the powers, as x approaches 2, I'm going to plug a 2 in for x. 2 squared becomes 4. Now, these rules, do not overthink them too much. What we can do is basically split up a function or a complex polynomial into different simple functions and just apply these rules. In this function, since x is going to c on both equations, the f of x and the g of x, we'll just say, okay, for f of x it would give you some number L, g of x would give you some number k. If I would take and multiply that function by some number, all I'm going to be doing is taking the answer and multiplying by that exact same number. Alright, if I'm taking 2 functions and adding them, like, okay, x squared plus 4x, all I can do is basically take the limits and I'm just going to add them together. It works for multiplication, it works for division, it works for powers. Basically, this whole thing sums up direct substitution. You're going to take the c value and plug it into x and simplify, unless you get zeros on the denominator. That's something we'll worry about in the next lesson. Okay, so we have this function here, the limit as x approaches 2 of 4x squared plus 3. We could go through, and this is the correct way of doing it. We'd break it down into, okay, let's do the limit of 4x squared plus the limit of 3. So we broke the addition up into 2 separate limits. Since we're multiplying by a constant, we can pull that constant out and just do the limit of x squared as it approaches 2. And leave the limit of 3 alone. Well, we know that x squared would be the same thing as 2 to the squared, or 2 to the second power, since we're going to take 2 and plug it in. And then we simplify. You guys might have noticed just right away, if I would have took 2 and plugged it in, we would have got the exact same answer. Direct substitution. Which is explained right here. Alright, now a big thing is what we can do and say if we have if P is a polynomial function and C is a real number, then R is a rational function given by R of x is equal to P of x over Q of x, and C is a real number such that Q of C does not equal 0. Then the limit as x approaches C of R of x equals R of C, which equals P over C and Q over C. Basically what this is saying is we can take a function and break it up into two functions over each other, which is going to be extremely important in the next section. We're going to go backwards from this. So what we could do here is that, as x approaches 1, this will work because the denominator does not equal 0 when x equals 1. If it did, we'd have to do something completely different. All we're going to do is plug in 1 to the top and 1 to the bottom and simplify. On the top, we'd get 4. The bottom, we get 2. 4 divided by 2 would be 2. Okay. Polynomial functions and rational functions are two of the three basic types of algebraic functions. The next theorem deals with the limit of the third type of algebraic function, the one that involves a radical. So, what we can say is basically here, more direct substitution that you're used to, no matter what degree it is. So if it's a square root, cube root, fourth root, fifth root, what we're going to do is take x and plug C in for x as the limit approaches it. Now the thing about this is the limit below is valid for all C when n is an odd and the value of C is greater than 0 when n is even. Alright, so this works for every odd function, every odd n power, because any cubes we can have negatives, but if this was ever n squared, n to the fourth root, we can never have C equal a negative number. Also, what we can do is do composite functions, or functions inside of functions. So if we know that as x approaches C of g of x, it equals L, and we're trying to find f of L as it approaches f of x, basically we're going to figure out 1, we'll plug it in for g of x, simplify it, and then plug that into f of x. So if we're going to find the limit of x squared plus 4 as the x approaches 0, all we're going to do is directly substitute in the 0 for x. We get x 0 squared plus 4, which equals 4. We could have split this up separately into two different radicals. Now this is just the inside part, so then we're going to plug that in and do the square root of 4, which is 2. Basically, we could have just done that right at the beginning and did not. Okay, 0 squared plus 4, which goes to 4, which equals 2. Same thing with the other one. We could have figured out the inside part here, simplified that down to 8, and then did just the cube root of 8. But I think it's easier for you guys to just see. We're going to plug in 3 there and do, okay, x to the 3 squared minus 10. Realize that's 8 and take the cube root of that. Most of this is stuff that I want to show you guys that all you're really doing is just plugging in the numbers for the majority of limits. Alright, and this also works for trig functions. So you guys can see that every single time all we're doing is replacing the x with a c. Now we will have to be careful if we ever get a value that does not exist. But for the first part of this section, we will not. Just direct substitution. You can see the tangent of 0, plug it in 0. X cosine x, we're going to plug in pi for those. So basically we're going to get pi times cosine of pi. Cosine of pi is negative 1, so that's how we get negative pi. And sine squared x, if you guys didn't know, here's a big thing that will be very helpful later on in the year. Sine squared x is the same thing as sine of x squared. So plug in 0, sine of 0 is 0, 0 squared is 0. Alright, this first section should be fairly easy. The next section I will do more problems worked out because they become a little bit more difficult. Good luck with this, and if you need any help, let me know.